In this video, we are going to deal with a problem related to electrostatics where we have a long thin wire of uniform linear charge density lambda, and it is coinciding with the y-axis of the coordinate system. So let me draw the figure first. So as far as the answer is concerned, we have so this is the y-axis and this is the x-axis more or less. So this is the x-axis and we have the y-axis over here. And we have a uniform charge distribution. Let me use another ink for that. We have a uniform charge distribution of charge density lambda. So I'm using a black ink over here. So this probably is the uniform charge distribution over here along the y-axis. And that continues, that's extending till infinity, I suppose, with no given dimensions available to us. So that's coinciding with the y-axis. Now we have a dipole, an electric dipole, which carries a charge plus q at a, b, 0 coordinates. So probably the x-axis here we have the a coordinate over here, and for y-axis we have the b coordinate over here. Let's say this is b. So this is a, b, and in the z-axis obviously it is 0. So this is a, b, 0, and there we have the plus q charge. And then just below that, exactly at the same distance, at a negative of b, we have a minus b and 0. That's where we have the negative q charge as per the question. Now we are to calculate the net moment of force experienced by the charges about the point A00. So this is the point A00. So about that point we need to calculate or obtain the moment of force. Now in order to obtain the moment of force, first we need to know that what are the forces experienced by the plus q and minus q charges, and in order to know that we need to calculate the electric field that is present at those points, the electric field due to the charge distribution. Now for that we can take the help of the Gauss theorem, where we have the cylindrical Gaussian surface. So if we construct a cylindrical Gaussian surface, we can calculate the electric field intensity. I'm going in detail in case you do not know how to obtain the electric field, or you do not know the expression for electric field intensity at those points. So we construct a cylindrical Gaussian surface symmetrical about that about the y-axis as well as the x-axis. So with that we have the radius of that cylinder to be equal to b. So this is the radius of that cylinder, and so the charges are enclosed within that cylindrical. Whatever charge lies on that surface, we will be able to determine the electric field at those points. So let's say for this charge at this point, the electric field intensity at a distance, perpendicular distance b, that will be equal to, from Gauss law we have E dot the entire surface area that is concerned, that we have pi 2 pi r here is the radius, which is b, times of the length, the entire length that is considered. The entire length, as we can see, is from extending from I beg your pardon, this the radius here is not b, it's actually a, because the extension is till a, so the distance is going to be a. So 2 pi a times of the length is going to be from b to minus b, so the entire length is going to be equal to 2b. So that is the curved surface area of the cylinder enclosing any charge lying within it, and that is going to enclose a certain amount of charge which is equal to lambda, which is the charge per unit length, multiplied with the given length, which is from b to minus b, which is going to be equal to 2b. So this is the amount of charge enclosed over epsilon naught. This is going to give me the value of the electric field. From that we can obtain the value of electric field. So 2b gets cancelled out, and what we are left with is E to be equal to lambda over 2 pi a times of epsilon naught. That is going to be the expression for the electric field at those points. Now, as far as the force is concerned, the force on the charge q, F on q, will be equal to, and that will be a repulsive force because the electric field is going to be a positive one for the positive charge distribution. So the repulsive force that is going to experience along this direction, so this is the force on q, and that is equal to q times of the electric field at that point. So that is going to be equal to lambda times of q over 2 pi a epsilon naught. Similarly, the negative charge is going to experience force along this direction. So this is F minus Q, and F minus Q is going to be obviously equal to, in the other way, but it's going the other way, but the value remains the same. That is lambda times of Q, 2 pi A times of epsilon naught. Now, with these two forces, the perpendicular distance that is separating the two forces is going to be equal to, well, that is 2b, of course. So the moment of force, or the torque that we can say, is equal to force, either of the force, because both the forces are same. So either of the force multiplied with the perpendicular distance that is separating the two forces. So that's going to be equal to lambda times of q over 2 pi a times of epsilon naught. Either of the force multiplied with perpendicular distance that is separating two forces is 2b. So the 2's get cancelled out. We have lambda over pi epsilon naught q b over a. Now, if we are to consider the dipole, or the dipole moment here is going to be q times of 2b. So if in case we were to include that 2b over there, we could have written this in another form. From here, we could have written it as lambda times of p, that is dipole moment, that taken over 2 pi a times of epsilon naught. So that's going to be the torque that is acting. You can either use this expression or this expression, whichever you are looking for. In case there was the dipole moment that was given, that is p, which is equal to q times of 2b, you can use this expression as well. So that's all from this video. Till next time, thank you for watching.